Modern physics makes a lot of mind-bending claims, but perhaps one of the craziest sounding is the idea that at every point in space, subatomic particles are coming into existence for a fleeting moment and then disappearing again. These flickering and ephemeral objects are called virtual particles. A lot's been written about them with varying degrees of accuracy. Let's take a deep dive and see how they're viewed by modern physics. The claim that empty space is full of effervescent particles seems pretty crazy. I mean, just look right there. Do you see particles appearing and disappearing? Nah, you don't. Neither do I. And you can be forgiven if you're skeptical. Of course, when we look, we're not seeing things on a truly tiny scale. Our eyes can't see things much smaller than 1/10 of a millimeter. And even using the most powerful scanning electron microscopes, we can only resolve things about the size of atoms. On the scale of virtual particles, these things are pretty big. And that means these biggish spaces contain lots of virtual particles. When you add up all the positive and negative effects of all of the virtual particles they contain, they average to basically zero. That's why virtual particles aren't obvious to everyone. However, there is no doubt that virtual particles are real. We can see them indirectly. If you take two conducting metal plates and place them near one another, and I'm talking really, really close, like separated by a distance equivalent to the diameter of a handful of atoms, those two plates will feel an attractive force. This is called the Casimir effect, and I've made videos about it. As always, the link is in the description. The Casimir effect works because the plates make it impossible for certain virtual particles to appear in the space between them, while outside, all particles can exist. This slight imbalance leads to a force that pushes the plates together. And here at Fermilab, we measure the spin properties of a subatomic particle called the muon. The particle's spin and electric charge mean the muon is also a tiny, tiny magnet. While the theory of 1930s quantum mechanics makes predictions of how strong the magnet should be, those predictions are wrong by a tiny bit, just 0.1%. This tiny shift is because each muon is surrounded by virtual particles, and the interaction between the muon and the virtual particles causes a tiny shift. The G-2 experiment actually measures this shift, and it does it incredibly precisely, like to 8 significant figures. The prediction and measurement agree quite well. And it turns out that there's a small disagreement in the last couple of digits, which could mean that there's more to learn about virtual particles, but that's the story for another time. I've made several videos about the G-2 experiment and the significance of the discrepancies. The links are in the description. But the real bottom line is that the Casimir effect and the accurate prediction of a 0.1% shift in the magnetic properties of muons are experimental proof that virtual particles are a real thing. But if they're real, what are they? And this is where things get tricky. After all, empty space surely looks empty, not like a flickering, chaotic mess. So let's start with the simplest way of thinking about virtual particles. We start out with a truly empty space, which includes absolutely nothing. It has zero energy. I mean, really, nothing at all. Then, according to the simple picture, from that nothing, a matter and antimatter electron appear. That's because even with virtual particles, some of the usual rules apply. In this case, matter and antimatter particles appear in pairs. The two then quickly recombine and go back to zero energy. The pattern then repeats over and over again, sometimes simultaneously, with more electrons and antimatter electrons, quarks and antimatter quarks, muons and antimatter muons, until the whole zoo of subatomic particles are represented, however briefly. The graphic sort of gives a sense of the vibe of what this model looks like, with things constantly appearing and disappearing. I guess you could maybe accept this, but let's just take a look at that first electron and antimatter electron. Initially, the space was empty with no energy. Then two particles appear, each with mass. Since mass equals energy, the result is that while the particles exist, the space has energy. And that seems to pose a problem, as the law of conservation of energy says that energy can't change. Yet here is a case where we started with no energy, then had energy come into existence before that energy disappeared again when the two particles annihilated. The usual explanation invokes the Heisenberg uncertainty principle. There are a couple of versions, but the relevant one is given here, and it says that the uncertainty in energy times the uncertainty in time must be bigger than a very small number. The relevance here is that it means that energy can change as long as the amount of time that happens is short. The graph says it all. If a lot of energy appears, that can only happen for a very short time. If the amount of energy that appears is small, it can persist for a longer amount of time. Mind you, longer still means very short. You'll never see it with your eye. So, the Heisenberg uncertainty principle is indeed relevant, and this explanation is real. But it does leave a false impression of particles appearing and disappearing. I mean, this does happen, but to better understand the modern meaning, we should revisit what we mean by the word particle. And that brings us to the present way of thinking. The name for the most modern theories of the quantum realm is called quantum field theory, or QFT. There are many examples of QFTs. For example, the theory that explains electromagnetism is called quantum electrodynamics, or QED. The theory that explains the strong force is called quantum chromodynamics, or QCD. And I've made videos talking about both of these specific theories. As usual, the links are in the description. But I don't want to talk about these specific theories. I want to talk about the basic idea of generic quantum field theory. The gist of all these QFTs is that empty space isn't actually empty. It's filled with fields. It has an electron field, a muon field, various quark fields, a photon field. In fact, there's a field for all of the known particles of the Standard Model. You might have seen this graphic that lists the known particles. That sounds super complicated, but let's start simple. Forget everything except the electron field. It fills space. In the classical world, it doesn't do anything. But in the quantum world, it can vibrate. And if it vibrates in exactly the right way, you have an electron. Indeed, that's what the electron is, a very specific vibration of the electron field. Precisely how it vibrates is determined by the properties of the field. It's like how the lowest note on a guitar string depends on the length of the string, the material it's made of, and how tightly it's stretched. So that's the key point. Electrons are specific vibrations of the electron field. Antimatter electrons are slightly different vibrations of the same field. Now we're getting to the main topic of this video, virtual particles. A quantum field can vibrate in more ways than the specific one that makes real particles. And when it vibrates in not quite the right way to make an electron, that's a virtual electron, although there is a corresponding vibration that also makes an antimatter electron. The same thing works with the photon field. Vibrations of the photon field make photons. Photons are different than electrons in that they can have any energy, but all real photons have zero mass. So for a real photon, the vibration pattern can have any energy as long as the energy vibration occurs in such a way that it has no mass. If the photon field vibrates in such a way that the vibration doesn't have zero mass, that's a virtual photon. And the same thing goes for all of the other particles. A very specific vibration of the up quark field makes up quarks, while other vibrations make virtual up quarks. It turns out that the various fields can interact with one another, but that's the topic of another video, so I won't go into that here. The bottom line is that quantum field theory postulates that space is full of a number of fields, each of which are vibrating in ways that don't create real particles, but the ensemble of vibrations are all the virtual particles that exist in that space. They are the white noise of the universe, a quantum hum, if you will. That's it. Particles are special vibrations of fields, and weird vibrations are virtual particles. That's the gist of quantum field theory and how it explains the world around us. It's probably worth noting that quantum field theory is just that, a theory. It explains physical effects. It could be that the real explanation of how the universe works is something else. What we know is true comes from the measurements, like scattering particles, measuring the Casimir effect, muon G-2 measurements, etc. Thus, the field theory is an idea, including the idea of vibrations, that's well tested, but it's important to remember that it's not the final word. Still, the idea is worth knowing. And I don't know about you, but I think that it's kind of good to know that the universe is sending us good vibes.